Other device connected. Okay, so this is being recorded. All right. So, confession time / concession time. I was annoyed on Friday that a lot of people weren't sure how to find eigenvalues. I thought this had been covered in linear algebra, but I spoke with a friend of mine from Serbia, and you'll see why her being Serbian is important. I was complaining about this, and she pointed out that in Serbia, she didn't learn how to do eigenvalues. Now, there are two reasons why this caused me to become more forgiving. One, of course, is, well, Christ, even Eastern Europe doesn't teach this, right? If Americans don't know this, then look, American education is rather special compared with Europe, Asia, the Middle East, Africa, South America, Central America, Australia, New Zealand, Pacific Islands, Atlantic Islands, Indian Islands, Greenland, and Antarctica. All right, there's a whole bunch of things that are different about us, and that's really something I could back up with facts if you just look at how the rest of the world uses tests and how we use tests. But the other thing is that apparently mathematicians just teach linear algebra a certain way. And you might be thinking, well, didn't you learn linear algebra that way? No, actually, I taught myself linear algebra because my linear algebra class was even worse than yours. So I just assumed that everybody else must do it better. So I had to teach myself linear algebra. So we're going to start from the beginning because I was persuaded that this is not just a thing about the difference between American education and European, Asian, African, Middle Eastern, South American, Central American, Asia, Pacific Island, Indian Island, Atlantic Island, Greenland, and Antarctica, but is in fact a physics versus math thing. All right. So we know that the recipe for an eigenvalue is this. You've got a matrix A, a vector V, and when A acts on V, you get an eigenvalue lambda multiplied by V. Or A minus lambda I acting on V equals 0. Now, this is a rather special equation because when you think about multiplying a matrix by a vector, it's always row dotted with column, row dotted with column, row dotted with column. And this is n by n. And so what we've got is n rows are orthogonal or perpendicular to our vector. We have a vector that is perpendicular or orthogonal to n other vectors. Now let's just think about this. In 3D, can anybody come up with a vector that's in 3D that's perpendicular to the x-axis and the y-axis and the z-axis?
Zero vector?
Pardon?
The zero vector?
Yes, the zero vector, but can you come up with any other vector?
This is me trying to be funny. The space-time vector.
Oh, well, fine, but now you're going into 4 dimensions, and I said in 3 dimensions. And that's the point. You can't do it in 3 dimensions, okay? You cannot have a vector that is perpendicular to n. You cannot have a vector in n dimensions that's perpendicular to all n directions. That's impossible. So the resolution to this is that these n rows must have some redundancy. Now, if this were a math class, they would start saying, we will theorem proof, we're going to talk about the rank of these matrices, we're going to talk about the dimensions of null spaces and stuff. I'm assuming you've already taken a class like that. I'm trying to translate this into what it really means. If V is an eigenvector, then there must be some redundancy between the different rows of A minus lambda I. That doesn't mean that there's redundancy among the rows of A. A might have no redundancy among its rows. A minus lambda I has redundancy. And as was discussed in more detail than I'm going to discuss right now, but as was discussed in linear algebra classes in more detail than I'm going to give right now, that means that the determinant of A minus lambda I must equal 0. All right, any questions on that idea so far?
Yeah, just real quick. So when I feel like I'm just getting a little ahead of myself, but when we have that matrix subtracted by the lambda I matrix, and we're trying to find our components for that vector, do we just augment our A minus lambda I vector with 0 and just solve for row echelon form?
You could. You absolutely could. But I'll tell you what people do in reality, what people tend to do in practice. Either you deal with matrices that have, say, maybe just 2 by 2 or 3 by 3, and you do it by hand with a few linear equations, or you feed it to a computer. Okay? That's the way that people tend to do this in practice in physics. Either they deal with some very simple matrices, 2 by 2, maybe 3 by 3, or they feed it to a computer. Let's do a 3 by 3 example. So A minus lambda I, and by the way, matrices like this show up all the time in solid state physics or in quantum computing. A minus lambda I equals the determinant of A minus lambda 1, 0, 1 minus lambda 1, 0, 1 minus lambda. So the determinant is that. And that's going to be equal to minus lambda times lambda squared minus 1, because we do this one and then we do that. And then minus 1 times 1 times minus lambda minus 0 from those two. And then the last one is just 0, so it doesn't matter. So we wind up with minus lambda cubed plus lambda plus lambda, because you've got -1, you got negative lambda times -1, and then -1 times negative lambda, or 2 lambda minus lambda cubed, or lambda times 2 minus lambda squared. So lambda is 0 or plus or minus square root of 2.
Isn't there a -1 in there too?
What?
Isn't there a -1 in there too? From the -1 times the 1 before the 1 minus lambda?
That was -1 times -1 times negative lambda.
Oh, times. Okay. Okay.
Yeah. All right, so now let's find an eigenvector. All right, let's start with 0. So we need to figure out a case where 0, 1, 0, 1, 0, 1, 0, 1, 0, acting on, I'll call this x, y, z equals 0, 0, 0. Okay, because that's 0 times x, y, z. Well, we know that if we just do the matrix multiplication, that is equal to y, x plus z, and y. So the first row gives us y equals 0. The second row gives us x plus z equals 0. The third row gives us y equals 0. And you see how there's some redundancy? That's built into this. That's the whole premise of the eigenvalue problem. There is redundancy. So all we can really say is that x plus z equals 0 or z equals minus x. So any vector of this form, x0 minus x, or x times 1, 0, -1. Some people get bothered calling it x because it looks too much like a coordinate. If you prefer, we could just say a times 1, 0, -1, because that's that which we call our variable would by any other name still be a variable. All right, so that's an eigenvector. And people say, well, then how should we write it when anything would do? Well, I asked you to find an eigenvector. That's an eigenvector. Somebody else could come along and say, well, what if I just wrote this? Yeah, that's still an eigenvector with eigenvalue 0. Somebody else comes along and says, what if I wrote this? That's still an eigenvector with eigenvalue 0. What if I wrote this, 3 minus 0.6i, because why not? And -3 plus 0.6i, because why not? That's still an eigenvector. So then the question becomes, so like, what like, do like, I like, write like? And the answer is that they're all eigenvectors, okay? What this really means is that the eigenvectors with eigenvalue 0 form a 1D vector space, okay? If we think about all of our vectors here as existing in a 3-dimensional space, then one axis of that space, and it's not the x-axis, it's going to be positive x and negative z. This axis here has lambda equals 0. Every vector along this axis is an eigenvector with lambda equals 0. And people say, but like, what if like we go in the opposite direction, like multiply by a minus sign? That is still an eigenvector with eigenvalue 0. Everything along that axis is an eigenvector with eigenvalue 0. Questions? Somebody must have a question. Feel free to state your question with a bunch of like and before it. I promise not to make fun of you this one time. Go ahead. If somebody's got a question, you must have a question, and you can put as many likes and in it as you want, and I won't say anything about it.
So what do you mean by a one-dimensional vector space? Like, yeah.
Okay, what I mean is that this set of vectors, this set of eigenvectors, obeys all the axioms of a vector space. If V1 and V2 are eigenvectors of A with eigenvalue 0, then A V1 plus B V2 is also an eigenvector of A with eigenvalue 0. Okay, a vector space is just a set of objects that can be combined in this linear manner, and you get another object from that space for any constants, for any scalars A and B. And there are a few other requirements besides closure under this operation. You have to have additive inverses. You have to have a 0 vector. I'm not a mathematician, so I don't have the axioms memorized in some minimal form. So I'm going to state them incorrectly if I try to state here is the minimum set of axioms with no redundancy. But that's the basic idea of them, that it's a set of objects that you can take linear combinations of and get another object in that set. We could do the same thing for another eigenvalue. we could decide that now we want to find eigenvalues square root of 2. 0, 1, 0, 1, 0, 1, 0, 1, 0, acting on x, y, z equals square root of 2 x, y, z. But we know that that's also equal to, just from doing the multiplication, let's see, y, x plus z, and y. So we're left with square root of 2 x equals y. Square root of 2 y equals x plus z. And square root of 2 z equals y. All right, and so what we're left with here is we could solve for all of this. We could just eliminate y, and we know that square root of 2x equals y, but so is square root of 2z. And so we can conclude that we've got a set of vectors where x equals z, which is different from what we had before. Before we had x and z were opposites. Now x equals z, and y is square root of 2z. So let's say we could write this vector in the following form: z square root of 2z and z equals z times 1 square root of 2, 1. And going back to my diagram, let's see, that's got positive projection onto all 3 directions. So that's going to be up and out of the page, or down and into the page. This is going to be the axis with lambda equals square root of 2. And so any vector along that axis in the positive direction or the negative direction will be a vector with an eigenvector with eigenvalues square root of 2. Questions? Something I want you to note here, which is not true of all matrices, but is true of these matrices, is that if I call this V1 and I call this V2, V1 dagger V2 is going to be x times 1, 0, negative 1, dotted with 1 square root of 2, 1, z equals x z times, let's see here, 1, and then 0 times square root of 2 is 0, minus 1 equals 0. So these two eigenvectors are orthogonal. That is something that often but not always happens. It is often but not always true that eigenvectors are orthogonal. Mathematicians would say that it's actually rarely true. That it only holds true for special classes of matrices, but it just so happens that this class of matrices, the classes of matrices for which these are guaranteed to be true, include 2 classes of matrices that we use all the time in physics: Hermitian matrices and unitary matrices. And we'll get to that proof later. For now, this is just an example, not a proof. Any questions?
Dr. Small.
Yeah.
So that last vector in the blue ink, is z the eigenvalue of that
No.
eigenvector?
Nope. Z is not an eigenvalue. The eigenvalue is square root of 2. Z is just some multiplicative constant. Could be 1, could be 0, could be minus 1, could be minus 17.3, could be 14,605,000, could be whatever.
And that is the eigenvector next to it.
This whole thing is an eigenvector, because if this is an eigenvector, then this multiplied by a constant is also an eigenvector,
Mhm.
or multiplied by a scalar.
Multiplied by scalar.
Okay. Then.
Pardon? I feel like I did something wrong there.
Professor, should it be just a 2 or a -2 instead of a square root of 2?
The eigenvalue is definitely square root of 2.
Oh.
Let's see about the vector element, the vector component. Square root of 2x equals y. So y is d squared 2x. Yeah, that's fine. And then we could do the same thing for negative square root of 2. And basically we just replace square root of 2 with negative square root of 2. And what we would finally get is that 1 minus square root of 2, 1 multiplied by some other scalar equals v3. And this would also be orthogonal to the other eigenvectors. It's orthogonal to this one because v3 dagger v2 is going to be 1 minus square root of 2, 1 multiplied by 1 square root of 2, 1. And that is 1 minus 2, because you got square root of 2 times square root of 2, plus 1 equals 0. And if we dot it with this other eigenvector, we've got 1 times 1, and we've got 0 times minus square root of 2, finally 1 times negative 1. Any questions?
Yeah, so is there a reason why you're using V3 dagger instead of V3 transpose if they're just the same thing?
Because I'm trying to be formal, kind of formal, and allow for the possibility that these are vectors with complex coefficients. In which case you have to do dagger rather than transpose. And a lot of the vectors that we use in quantum mechanics have, a lot of the vectors that we use in quantum mechanics have complex components or coefficients in there. So I want to be general and allow for that possibility. All right, let's talk a little bit more about the redundancy. This provides a simple way of understanding why it is that a matrix is not invertible if its determinant is 0. A basic fact is that the determinant of a matrix is equal to lambda 1 times lambda 2 times lambda 3 all the way to lambda n. It's the product of all of the eigenvalues. Another fact is that if our eigenvectors form a complete set, and remember that in linear algebra, a complete set was a set of vectors such that you could use it as a basis for the vector space. Then I could write any vector x in this form. The sum from k equals 1 to n of c sub k v sub k, where v sub k is an eigenvector of A. Now, keep in mind, it's not always guaranteed to be possible. There are plenty of matrices that don't have a complete set of eigenvectors. But if they have a complete set of eigenvectors, then we can do that. So if we could do that, then let's consider the classic form in which mathematicians write out a system of linear equations. All right, well, x, like I said, can be written in this form, and b could be written as the sum from k equals 1 to n of bk, vk. So we've got a set of coefficients, a matrix of coefficients, acting on a vector with components x1, x2, xn equals b1, b2, bn. Or I could rewrite this as ax equals the sum from k equals 1 to n of ck a vk. Because if x is the sum of a whole bunch of vectors, if x can be written by just adding up a whole bunch of vectors, say these vectors, then ax could be written by just taking a and having a act on each and every one of those vectors. What do we know about a vk? What do we know about the matrix A acting on the eigenvector vk? Anyone?
It won't do anything to the vector.
It doesn't change it. We just get lambda k. Well, I mean, I guess it does change it. It multiplies it by a constant, but it doesn't do anything to its direction. So we get lambda k vk. And we know that this could be written as the sum of bk vk. And these vk's form a complete set. Because they form a complete set, that means that ck lambda k equals bk. Which is great most of the time, unless lambda k equals 0. Any questions? This is why you can't invert a matrix that has 0 determinant, because one of the eigenvalues, excuse me, is at least one of the eigenvalues is 0, which means that you can't really work backwards. You know, if I look at a matrix acting on a vector and what new vector I get out, I can look at the new vector and I can say, okay, the new vector has this much of the first eigenvector in it. And I can say, all right, that new vector must be equal to eigenvalue 1 multiplied by whatever part of the original vector was eigenvector 1. So I can work backwards and say, okay, the part that has eigenvector 1 in the new vector, if I divide out eigenvalue lambda 1, then I get out whatever part of the old vector was parallel to eigenvector 1. Yeah, I can work backwards. Like if I've got some operation that takes the x component of a vector and multiplies it by 2, and I look at my new vector and I see, hey, it has x component 5, then I know that the original vector must have had x component 2.5, because the matrix takes the x component. This is my matrix. If A was equal to, let's say, 2, 3, 4, and then zeros off diagonal, then A operating on x, y, z equals 2x, 3y, 4z. So I could just look at my new vector and I could say, okay, the x component of my new vector is, I don't know, 5, 10, and 100. So I could say, all right, well, 2x equals 5. So x is 2.5. And 3y equals 10. So y is 0.333, etc. And 4z equals 100, so z is 25. That would be easy. But if one of the eigenvalues was 0, and here I'm using diagonal matrices because they're easy, and we'll get to why I'm allowed to use that as an example. If A equals that, then A acting on x, y, z is just 0, 4y, 10z. We have no way of figuring out what the x component of the original vector was. Absolutely no way. Maybe you could say, well, the new vector had x component 0. Why can't we just say that the old vector had x component 0? Well, maybe the old vector had x component 0, but we don't actually know that. All right, that's a matrix that basically erases all the fingerprints of the x component. If you think about solving equations as solving a mystery, you know, the equation is expressing a mystery. We want to know what the values of x, y, and z are. We have to work backwards like a detective. A matrix with the eigenvalue 0 is erasing some of the evidence. Okay? It's the crooked accountant that was hired to make some of the money disappear. That's what a matrix with eigenvalue 0 is. It's engaging in destruction of evidence, and you can't work backwards and figure out what actually happened. Questions?
So for your, I'm just trying to look at your handwriting here. So your A vector augmented with another vector, that's just X as a column vector, correct?
My A vector, you think you mean my A matrix acts on a column vector. X in this case is an element of a column vector, X, Y, Z.
Okay, got it. Thank you.
Yeah, these are just elements of a column vector. Other questions?
Where did you get the vector 5, 10, and 100?
It's just an example.
Okay, thanks.
I was just saying that if this happened to be our matrix, and this just happened to be our new vector, we could figure out our old vector. In some sense, solving equations is just solving riddles, solving mysteries. You know, you're working backwards from a set of numbers to figure out what number, from the output to figure out what the inputs were. The inputs are one vector, the outputs are another vector. In a mystery, the inputs are Colonel Mustard in the study with the revolver, and the output is a dead body and a bunch of clues, right? And you're trying to work out, was it Colonel Mustard who committed the murder? So our lesson so far should be that when a matrix has a complete set of eigenvectors, we have an easy way to see if that if one of them is 0, it's not invertible. And 2, we can derive a lot of facts easily. We can easily make sense of linear equations if eigenvectors are linearly independent. Now, some facts about important classes of matrices. Let's start with Hermitian matrices. I claim that all eigenvalues are real. And the way to see that is, let's have H a Hermitian matrix. H dagger equals H. Therefore, H is Hermitian. And H times VI is lambda I VI. That's just a fact. That's just telling us that it's an eigenvector with eigenvalue lambda I. Well, I could take the dagger of both sides. HVI, whole thing dagger, would be VI dagger, H dagger. But that would be, of course, VI dagger H, because H is Hermitian. But that's also the dagger of this thing here. So it's also lambda I star VI dagger. So far, nothing special. But now let's take VI dagger H VI. All right, well, that's equal to, we can write that thing two different ways. We could start with this. If we work from this perspective, we get that that is just lambda I star VI dagger VI, because we took these two things, we turned them into this. But that's also equal to, if I worked from over here, VI dagger VI lambda I, starting from here, because we know that HVI is lambda I VI, and VI dagger H is lambda I star VI dagger. I've got this in both expressions. Oops, sorry. This in both expressions. So lambda I star equals lambda I. Now, the only way that something can be equal to its complex conjugate is if it's real. Questions? This is important because in quantum mechanics, we use Hermitian matrices all the time. And the eigenvalues of those Hermitian matrices turn out to be real numbers, which means that our predictions about the physical universe in the end involve real numbers. Even though there's a whole bunch of complex numbers going into it, after you've done all of the calculations, in the very end, a bunch of things will cancel out and you will get real numbers, which is nice. I enjoy knowing that my position is a real number, not an imaginary number. If my position was an imaginary number, I'd be even more lost than I am right now in my life. Besides all of the eigenvectors being real, all the eigenvalues, excuse me, all the eigenvalues being real, the eigenvectors are orthogonal. And I'm only going to prove that for the case of a non-degenerate matrix. I'm not going to prove that for the case of degenerate eigenvalues. If you want to prove it for degenerate eigenvalues, frankly, you should take Math 4190. It's a much longer proof. But they do all of that stuff the right way in there. Eigenvectors are orthogonal. So let's again start with the fact that HVI equals lambda I VI, and HVJ equals lambda J VJ, but HVJ dagger equals VJ dagger H. And I'm leaving out the H dagger because H dagger equals H. And that is just lambda J VJ dagger because all eigenvalues of H are real. Now we're again going to form a sandwich. Now up here we formed a sandwich. We sandwiched H between the an eigenvector and the Hermitian conjugate of that eigenvector. As people sometimes call it the adjoint. Now I'm going to take VJ dagger H VI. And just like I did before, I can write that two different ways. If I start from this, I can say that that is lambda J VJ dagger, VI. But if I start with this, that is equal to lambda I VI, All right, so I can either get two of these quantities, I can get two of these quantities from whichever pairing I want. And in the end, all of these things have to be the same. These two things have to cancel. Well, no, wait, sorry. So what I'm left with is that lambda J VJ dagger VI equals lambda I VJ dagger VI, or lambda J minus lambda I VJ dagger VI equals 0. This is non-zero because we're only considering non-degenerate eigenvalues, which means that this is 0. Questions? An obvious question should be, what about degenerate cases? What if, oops, sorry, there's this button on my stylus that I keep hitting. What if H has degenerate eigenvalues? I'm just going to state the spectral theorem and then I'm going to illustrate it with an example. The spectral theorem, if you want to see a proof, again, you should take the upper division linear algebra course. Any Hermitian matrix has a set of n orthonormal eigenvectors. Orthonormal means that they're all orthogonal to each other and they're all normalized, i.e. VI dagger VJ equals 0 if I is not equal to J. So that means that different eigenvectors are orthogonal to each other, and 1 if I equals J, which means that individual eigenvectors have length 1. They are normalized. Now, if I have degenerate eigenvalues, if they're degenerate of order m, that just means that order m degeneracy means, well, m-fold, like that if you were to factor the characteristic polynomial, that eigenvalue shows up m times. Like if you're factoring the characteristic polynomial, you get lambda minus something squared instead of just lambda minus something, or lambda minus something cubed, or lambda minus something to the fourth, depending on the order of degeneracy.
Dr. Small.
Yeah,
So you're saying the degeneracy relates to the multiplicity?
yeah, degeneracy and multiplicity are two words for the same thing.
Okay, got it.
Then the eigenvectors span a space of dimension m. So let me give you an example which is related to a matrix that you worked with on Friday. Similar to one of those matrices. Let's say that H is equal to 1, 0, 0, 0, 0, 0, 1, 1, 0. This is a really simple matrix, but it will show up in quantum mechanics sometimes. It could show up in quantum computing, and it illustrates the point quite nicely. H minus lambda I would be 1 minus lambda 0, 0, 0, 0 minus lambda 1, 1 minus lambda. So the determinant of H minus lambda I would be 1 minus lambda times this subdeterminant. And this subdeterminant was written so sloppy, that should be a minus lambda there. So we're going to get lambda squared minus 1. So lambda could be 1 from this, or 1 from this. 1, 1, or minus 1. So let's try to find the eigenvectors with eigenvalue 1. Usually we wind up with enough redundancy that we have one undetermined constant. But the spectral theorem is telling us that those eigenvectors are going to span a two-dimensional space, which means that we're going to have two undetermined constants. And you'll see 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, acting on A, B, C is equal to, well, the eigenvalue is 1, A, B, C. But we also know that that is just from having the matrix act on the vector A, then having this row act on the vector, we get C, and having this row act on the vector, we get B. So ABC equals ACB, and I just realized there are jokes we could be making about TV coverage of Senate hearings, but I swear I did not choose ACB to spell out initials. Anyway, so A equals A for any A, and B equals C from this row, and C equals B from this row. So our eigenvectors are of the form A, B, B, which I could write as A times 1, 0, 0 plus B times 0, 1, 1. So A times this possible eigenvector plus B times that possible eigenvector. Or really, if I wanted to normalize it, I might choose to write this as C1 times 1, 0, 0 plus C2 times 1 over square root of 2, 0, 1, 1. And the reason I would do that is that then we've got length 1. That would be a more conventional way of writing it out, just so everything has length 1, but they're both mathematically valid ways of writing it out. Question?
Professor,
right next to where you have lambda equals 1 in that matrix over there, I think you inputted some of the values for lambda wrong. The one in the center should be -1, and then so should the one on the bottom right.
Oh, no, that's if I was writing out h minus lambda I. But here I'm just writing h times the vector equals 1.
Oh, okay. Thank you.
Professor, I had a question.
Yeah, this is supposed to be HV, not h minus lambda I acting on V.
I was wondering if the spectral theorem could be restated to say that any Hermitian matrix has equal number eigenvectors and eigenvalues.
Yes, yes, the spectral theorem can be written as saying that it has a complete set, that there's an equal number of eigenvalues and eigenvectors. Keeping in mind that some eigenvalues have multiplicity greater than 1. And all the eigenvalues, all the eigenvectors, excuse me, corresponding to distinct eigenvalues are orthogonal to each other. And eigenvectors that correspond to eigenvalues with multiplicity m span an m-dimensional space. And here we've got multiplicity 2. So we get a 2D space. I'm not going to do it for higher order multiplicity, but if you were to construct a matrix that had a threefold degenerate eigenvalue or an eigenvalue with threefold multiplicity, then we could arrange them into a three-dimensional space. And just for completeness, to further illustrate the spectral theorem, let's take the -1 eigenvalue. So now let's say lambda equals -1. 1, 0, 0, 0, 0, 0, 1, 1, 0, acting on A, B, C equals -1, A, B, C equals, well, A, C, B. So now what we get from the top row, -A equals A, that's impossible unless A equals 0. From the middle row, -B equals C. And from the bottom row, -C equals B. These are redundant and repetitive. They are repetitive and redundant, which means that our eigenvector, B3, could be written as 1 over square root of 2 times 0, 1, -1. And again, that's square root of 2, 1 over square root of 2, excuse me, comes from normalizing the eigenvector. Any questions? Anyone? Somebody must have a question.
I have a question.
Yeah.
Does a normalized eigenvector always have a length 1?
Did you ask if an eigenvector has length 1 or a normalized eigenvector?
A normalized eigenvector.
Yes, normalized means length 1. An eigenvector doesn't have to have length 1 because you can multiply an eigenvector by any scalar you want and get another eigenvector. But to be normalized means that you have length 1. That's the definition of normalized. Other questions?
So when you, let's say we were doing a homework or maybe a test and you say to normalize one of our vectors, we can just divide that by the magnitude and that's pretty much it, right?
That's how you normalize a vector. Take the vector, divide by its length, and you get back a new vector that points in the same direction but has length 1. Let's say we had a vector to normalize. Let's say we had a vector 3, 4, 12. Then, or 3i, 4, 12, just so that the dagger is not a completely trivial thing. Then v dagger v would be minus 3i, 4, 12, dotted with 3i, 4, 12. So we'd get minus 3i times 3i plus 4 times 4 plus 12 times 12. We would get 9 plus 16 plus 144, or 169, which is 13 squared. And I deliberately chose those to make the math easy. Then I could normalize it. V over 13 would be 3i over 13, 4 over 13, and 12 over 13. And that would be a normalized vector. Other questions? Okay. Let's talk about unitary matrices a little bit. And again, I'm only going to consider unitary matrices with non-degenerate eigenvalues. But it can be proved that everything I'm saying also applies to unitary matrices with degenerate eigenvalues. Remember the definition of a unitary matrix. U dagger U is the identity matrix. And I claim that all of the eigenvalues are of the form e to the I phi sub j. All right, that any eigenvalue can be written as e to the I times some real number. So it's just some number on the unit circle. Okay? 1 minus 1 I minus I. And we're going to prove that. U acting on V sub j is lambda j Vj. And then, as we've been doing the whole time, U Vj, whole thing dagger, equals, well, whenever you take the Hermitian conjugate, you just reverse the order and conjugate. But we know that that's also equal to lambda j star Vj dagger, because we take the conjugate of, this comes from the left side, this comes from conjugating the right side. So then we could take Vj dagger U dagger U Vk, all right? So, well, no, actually I'll do U Vj, my bad. We'll get to Vk in a minute. So now we could take this. We could take the inner product of Vj dagger U dagger U Vj, and we know that what we would get is, on the one hand, lambda j star Vj dagger lambda j Vj. That just comes from taking this and this. But on the other hand, what do you know about U dagger U?
It's the
Equal I.
identity.
It's the identity matrix. So it must be that Vj dagger Vj is just equal to lambda j star lambda j vj dagger vj. And then vj dagger vj tweeted something terrible, so we cancel it. And we're left with 1 equals lambda j star lambda j, or the absolute value of lambda j squared equals 1, which means that it's got to be on the unit circle there. Any questions? Now let's prove the orthogonality of the eigenvectors. Okay, so now let's again use the fact that UVJ equals lambda j vj, UVK equals lambda k vk, and UVK dagger would be equal to, on the one hand, VK dagger U dagger. That's just how conjugation, Hermitian conjugation works for products. But that would also be lambda k star VK dagger. And so VK dagger, U dagger, UVJ, that would have to be, on the one hand, lambda k star VK dagger lambda j VJ, or lambda k star lambda j VK dagger VJ, or using this fact up here that it's just e to the I times some phase, I could write that as e to the I times phi sub j minus phi sub k. You're thinking, why is it minus phi sub k? Because I conjugated this one, which is going to flip the sign of that phase up in the exponent. Oops, and that shouldn't be an equal sign. All right, so that's one way to write it, to just proceed from all of this logic. But we also know that this is an identity matrix. So this should just be VK dagger VJ. And what we're left with is that VK dagger V sub j is equal to e to the I times phi j minus phi k, VK dagger VJ. And this thing here is not 1 because we assumed that it's non-degenerate. That was our assumption going in. All right, I said I was only going to prove this for non-degenerate cases. So this is not 1. So we're taking this inner product, we're multiplying it by something other than 1, and we're getting the original inner product back. Whenever you take a number and multiply it by something other than 1 and get the same number back, that number has to be 0. And again, if they're degenerate, it can be proved, although I won't prove it here, that you can still construct a, if you've got an eigenvalue with, say, multiplicity 2 or degeneracy 2, then you can construct a two-dimensional space of eigenvectors that all have whatever that degenerate eigenvalue is. And that two-dimensional space of eigenvectors is orthogonal to all of the eigenvectors corresponding to other eigenvalues. Any questions? Anyone? All right, I've analyzed for you the nature of the eigenvalues and eigenvectors for the most important types of matrices that you will encounter next year in quantum mechanics. Now I want to tell you a fact about eigenvalues and eigenvectors of a matrix, and since I might have to rush through it, we're going to have to continue this on Wednesday, which means the problem set 6 is due Friday. Follow-up is due Monday. Now, I'm not delaying any of the practice assignments any further because we're not going to spend much of Wednesday on this. We're going to wrap this up on Wednesday, and then we're going to start the vector material, the vector calculus material that we need to cover. So the next practice assignment is still due Wednesday. The following practice assignment will still be due Monday. But problem set 6 will be due Friday, and problem set 7 will be shorter. To make up for the compressed time frame between problem sets. Oops. But I at least want to start this because it turns out that eigenvalues are significant for more than just showing up in a lot of physics problems. I mean, that's already a very good reason to care about them. They do show up in a lot of physics problems, and so we do have to know how to solve them. But eigenvectors are almost like, eigenvalues, excuse me, are almost like the chemical elements of a matrix, and eigenvectors are almost like the bonds. I make the following claim, which I will not prove. Again, take an advanced linear algebra class for this. I'm going to show you what it means and how we can use it. That most matrices including all Hermitian, unitary, and anti-Hermitian matrices. Those are the 3 most common types of matrices in quantum mechanics. Can be written as A is our matrix equals some matrix S. This is called a transformation matrix. Actually, writing down the transformation matrix is usually less important than knowing it exists. And then a diagonal matrix where along the diagonal are all of the eigenvalues. And off diagonal are just a bunch of zeros. And then you follow it up with s to the minus 1. So what we've got here is we've got a new way of writing out a matrix, a way that kind of picks the matrix apart. It says we've got some unknown transformation matrix. We've got a diagonal matrix with all of the eigenvalues in it. And then we've got another transformation matrix, which is related to the first transformation matrix. It's just the inverse of the other transformation matrix. Why do I care? Why is this useful? Well, here's one reason why it's useful. If I write this in the form A equals s to the minus 1 ds, where d just means diagonal, then a squared is s to the minus 1 ds s to the minus 1 sorry. Blah. S to the minus 1. All right. Now what's S to the minus 1 S? Don't overthink it.
Identity matrix.
Identity. So I've got S d squared S to the minus 1. And d squared is really easy to compute because we're just squaring a diagonal matrix. You got lambda 1 squared, lambda 2 squared, lambda 3 squared, all the way down to lambda n squared. Zero's off diagonal. And a cubed is S d S to the minus 1, S d S to the minus 1, S d S to the minus 1. That's identity, and that's identity. So lo and behold, I've got S d cubed S to the minus 1. And d cubed, again, is real easy. It's just lambda 1 cubed, lambda 2 cubed, lambda 3 cubed, all the way down to lambda n cubed, 0, 0. And I could keep on going. So if I want to compute functions of matrices that involve polynomials in those matrices, well, this is a really easy way to work with the matrix. And in fact, on the homework, you've got something that involves matrix exponentials, where we say that e to the a is equal to the identity matrix plus a squared over 2 factorial plus a cubed over 3 factorial plus a to the 4th over 4 factorial, etc. And that also turns out to be really important in quantum mechanics. And if you try to crank through this in general, this is really difficult. But if we take advantage of the fact that the matrix can be diagonalized, and that's what it means to write in this form. It means that we diagonalize the matrix. It means that we, that's the name for writing in this form. Diagonalization is just a way of saying that we take some matrix, which could look really elaborate, and we write it in this form. A part that, frankly, we don't need to use that much. Another part whose existence often matters more than its detailed form. And then the part that we actually do all of the algebra on. Now it's easy to prove that this has all of, if this is equal to A, then it better have same eigenvalues. And it better satisfy the same characteristic polynomial. That's easy to prove because the determinant of S d S to the minus 1 minus lambda I is equal to the determinant of S times d S to the minus 1 minus lambda. Actually, let me skipping a step there. SIS to the minus 1, well, multiplying I by something doesn't change it. So this is just SS to the minus 1, which is I. Okay, so this is a very fancy way of writing out I, which means that I could pull out an S on the left. And an S to the minus 1 on the right. And I haven't changed the order of any multiplications. And what do we know about the determinant of a product?
It's the product of the determinant, right?
Yep. So this is going to be equal to the determinant of S times the determinant of D minus lambda I times the determinant of S inverse. And what do we know about the determinant of an inverse?
It's minus the determinant of the original.
Not quite. It's 1 over the determinant of the original.
Oh, and isn't there an adjoint in there too somewhere?
No, an adjoint only, if you transpose a matrix, you don't change the determinant. If you take a complex conjugate of a matrix, then you conjugate its determinant. So these cancel out, and we're left with the determinant of D minus lambda I. And let's say that, this is the last thing I'm going to do. Let's say that lambda just happens to equal lambda 2. Then what we've got is just an example. Then all of this becomes the determinant of lambda 1 minus lambda 2, lambda 2 minus lambda 2, lambda 3 minus lambda 2, all the way to lambda n minus lambda 2. And this is 0. The rest of these could be non-zero, or maybe there's some degeneracy, and so some of them are 0. But either way, we've got a 0 here. And when we take the determinant of submatrices, hey, eventually we get a 0, because we get this times a 0 times the next submatrix determinant. So all of that is 0, and it satisfies the characteristic equation. And what I'm going to do next time is I'm going to show you how this encodes the eigenvectors as well as the eigenvalues, how writing it this way encodes everything about the matrix. And so the eigenvalues become like the chemical elements, and the eigenvectors become the ways in which those eigenvalues are joined, or the bonds between the elements. So it's a way of analyzing a matrix in the same way that you would analyze a molecule. What is it made out of, and how does it all fit together? And we'll continue with that on Wednesday. And again, just to confirm, on Wednesday, the only thing you need to turn in is the next practice assignment. The problem set will be due Friday, and the follow-up will be due on Monday. And I'll push back all of those due dates in Blackboard in a few minutes. And I will see you on Wednesday or in my usual office hours. Have a good day.
Yep. See you soon, Dr. Small. Thanks.
Bye.
Thank you, Dr. Small.
You're welcome.
Dr. Small, I had a question about this coming practice assignment.
Yeah.
For the first problem, you give us a scalar function, and you ask us to take the curl and divergence of it.
What did I ask? Did I ask for the curl of a scalar function, or did
And
I
the divergence, yeah.
curl of its gradient?
Oh, curl of its gradient. My bad. Yeah.
Yeah.
I see. Thank you.
Thank you, Dr. Small.
You're welcome.
Professor, I had a question about when you said that eigenvectors are orthogonal, and you told us to take Math 4190 to see the proof.
Yeah.
I was thinking about it, and I was like, well, don't eigenvectors have to be orthogonal, or else they're just like a linear combination of the parallel ones?
Linear independence is not the same thing as orthogonality.
Huh.
All right, so if I have, hang on, something just popped up on my screen I'm trying to get rid of. So if I have two vectors like this, these two vectors are not orthogonal. They are linearly independent.
Mm-hmm.
So
hey, how are they not? I thought orthogonal was if they crossed.
Orthogonality means perpendicular. It means that their inner product is 0.
Oh, okay. All right, then that's where I'm mistaken.
Yeah.
Okay, And then another thing, because I know if we have an eigenvector in like in a space and we do like a linear transformation on it, if that eigenvector pertains to that linear transformation, then that eigenvector stays the same after the transformation, right?
What do you mean if that eigenvector pertains to that linear transformation?
Because isn't a linear transformation just a matrix?
A matrix is a type of linear transformation. You can represent linear transformation with matrices. What are you trying to say? Are you trying to say that changes of basis don't really change the relationships between eigenvectors?
Yes.
Yeah, basically rotations do not change the relationships between eigenvectors. If I've got, say, two eigenvectors here, do a change of basis. These two eigenvectors were orthogonal before, they remain orthogonal as I do a change of basis. It could be that now these two eigenvectors, if I try to write them out in a new basis, they look really complicated, but they still have the same relationship between each other that they had before.
Okay. And so then my next question is, if we had a vector that was built on the eigenvectors, is that still an eigenvector?
Not necessarily. If they're degenerate eigenvectors, then yes. But let's say that I've got a really simple matrix. All right. So the vectors are 0, 1, and 1, 0. Okay. And so I take 3 times 1, 0 plus 4 times 0, 1. All right, well, this is an eigenvector, and this is an eigenvector.
Right.
But A times 3, 4 is equal to 3, 8, which is not equal to some constant times 3, 4.
Okay. All righty. Thank you, Professor.
You're welcome.